For problem 54, we have a crate on an incline on a plane tilted at an angle of 25 degrees above the horizontal, and we know that the coefficient of kinetic friction, mu subscript k, is 0.19. We should determine the acceleration of the crate as it slides down the plane, and then answer the question: if the crate starts from rest 8.15 meters up along the plane from its base, what will the crate's speed be when it reaches the bottom of the incline? So the first part of the problem, determine the acceleration of the crate. Given the incline plane and knowing the coefficient of kinetic friction, I'm thinking Newton's laws, Newton's second law, and the free body diagram that accompanies that, and solving for acceleration using Newton's second law. For part B, however, given the length of the plane, so 8.15 meters, and being asked for the crate's speed at the bottom of the plane, that sure sounds like a kinematics problem to me. That's kinematics. Once we know the acceleration, constant acceleration. So we're going to be thinking about those equations for distance traveled with constant acceleration. In this case, we'll know distance, acceleration, and the starting speed, and we want to know the ending speed. So the v squared equation is probably what we'll choose. So we sort of have two parts to the question, two kind of concepts, Newton's second law and then kinematics equations. And of course, starting with Newton's second law, we want to start with a free body diagram. So there's my dot, there's my incline, and that becomes my x-axis. And we always do that because we expect that box to stay on the incline as it rolls down the hill. Acting on the box, on the crate, is pull of gravity, straight down. And that's a number we can know because, no, just kidding, we don't know. We don't know the mass of the crate. So we will work without the mass of the crate until we can work around not knowing it. We have normal force pushing up, normal to the plane, F subscript N. And then we have friction opposing the slide down the hill, F subscript K, curvy F subscript K for friction. So we have no other objects touching the crate, just the plane touches the crate. And so that's it. So now I know, of course, I need to decompose that force of gravity into its y component, FGY. And I sure didn't quite make those equal in length, but we know those will be equal in length. And FGX. And I know that the angle between y and the vertical is the same as the angle of inclination. My diagram's getting awfully messy, but that angle is 25 degrees. So FGX is equal to FG times sine of 25 degrees. It is opposite to the angle. And that, of course, is mg sine 25. FGY is equal to FG times cosine of 25 degrees because it is adjacent to the 25 degree angle, and that is mg cosine 25. We're sort of stuck there because we don't know the mass of the box. For this problem, we did need to really know both the x and y components of the pull of gravity because we'll be calculating the force of kinetic friction, which is equal to mu sub k times normal force. And we expect the normal force to be in balance with the y component of gravity. So the acceleration of the box is equal to the net force on the box divided by mass. There's our statement of Newton's second law. The acceleration must be equal to, in the down the hill, which I've decided is positive x direction, the x component of the pull of gravity, minus, in the uphill, or negative x direction, the force of kinetic friction. Those are the two forces in the x direction, down the hill positive, up the hill negative. All of that needs to be divided by the mass of the box. So I'm going to have to take part B somewhere else. I need more room. So we've got the acceleration equal to the x component of gravity, mg sine 25. I just see that I wrote 55, but that should have been a 25. Minus mu sub k times normal force, but normal force is FGY, so mg cosine 25 all divided by mass. And thankfully, I can factor mass out of the numerator of the equation and then cancel the numerator mass with the denominator mass. So I end up with g times sine of 25. Oh, g I can factor out as well. Sine of 25 minus mu sub k, which I forgot to write in, but is 0.19 times cosine of 25, close parentheses. And so I can calculate that if my phone will cooperate with calculating trig functions. So let's see, cosine of 25 degrees. I don't actually know how to use my phone to do trig. So I'm grabbing one of the school calculators. Okay, cosine of 25 degrees, and I am in degrees, times 0.19, and then sine of 25 degrees, and then subtracting, nope, it's not going to work that way. Okay, sine of 25 degrees, subtracting 0.19 times cosine of 25 degrees. All right, 0.2504, etc., and that whole thing gets multiplied by g by 9.8 meters per second squared. So we have a downhill acceleration of 2.45 meters per second squared. All right, down the hill is positive. So now for part B. The crate starts at rest, so V naught is 0 meters per second. It travels 8.15 meters down the ramp. So x naught can be 0. X final is 8.15. The ending velocity is unknown. That's what we want to know. What's the speed at the bottom of the incline? And the whole time it's accelerating at 2.45 meters per second squared. So the v squared equation is what we want to use. V final is equal to the square root of v0 squared, that's 0. Right, the starting speed is 0 plus 2 times the acceleration times delta x. So multiply the acceleration by 2, multiply by 8.15, take the square root, and we find that its ending speed is plus or minus 6.32 meters per second. I choose plus because plus is down the hill.